Okay, ladies and gentlemen, let's talk about something called apparent weight. Um, Imagine a silly situation, and after Thanksgiving, of course, it's maybe a little apropos. Imagine you are in a an elevator. Yeah, that's an elevator. And while you're in that elevator, you're on a bathroom scale, and you are looking at your weight. Now, of course, it's after Thanksgiving. Maybe we don't do this, but but if you're in this elevator and the elevator is absolutely still, just not moving, it's just like as if the bathroom scale were in your house, and you get on the scale and it would read your weight. Now, of course, we are in physics class, so we are going to do our weight not in pounds, but in newtons. So let's say that your mass is 51 kilograms, which means that the scale would actually make a reading of 500 newtons. That's what the scale would read. And so this 500 newtons is just your weight. Of course, that's not actually what the scale's reading, though. Your scale says 500. Yes, you do, in fact and indeed, have a weight of 500. That is true. But your scale actually reads, hold on, I gotta undo this. Your scale actually reads the normal force. So your scale's going to read the normal force, but if you're just sitting there, not moving, absolutely still, your normal force and your gravitation, they're going to be equal but opposite. So the normal force is going to be 500 newtons. Okay. So, yeah, what I'm telling you is your bathroom scale doesn't actually measure your actual weight. It measures the normal force, but the normal force equals the weight if you're standing still. Fine. But what if that elevator started to move? What if you're in that elevator on that scale and you press the button and you start to move from rest? So let's say that you suddenly press upward. You say you're on the bottom floor. And so what happens is the elevator begins to move upward. But of course, when that elevator is moving upward, it's also going to get the scale to move upward. Now, what's that doing? Well, when this tries to move upward, remember, you want to stay still, right? Because of inertia. You don't want to move. And in order for you to accelerate upward, well, you're not accelerating upward, but if we were to get you to accelerate upward, well, that means that if you look at your free body diagram, that your normal force and your gravitation force, they can't be equal anymore. Because if they're equal, you're not going to accelerate upward, right? You only can accelerate if you have unbalanced forces. And so we need, in order to move upward, we need the normal force to be bigger than gravity. And that's what happens, right? So when you press that button and you make that whole system start to, oopsie, I broke it, apparently. When you make that start to rise, this whole elevator is trying to push through you. And so it's that normal force. Yeah, the normal force of the scales, the bottom of the scale is pushing, that surface is pushing on you upward. Of course, that's because the elevator was pushing on the scale upward also. But that scale is physically trying to go through you, right? It's pressing into your legs. And so you would need, depending on the acceleration, moving upward, that force is going to be greater than your gravity. So maybe the normal force ends up being 600 newtons. That means the scale's going to read 600 newtons as it tries to push you up. And if you've ever been on an elevator and you've pushed the up button, you might notice, you feel it in your knees, like especially one of those express elevators that moves pretty quickly. You might feel it in your knees. You're going to feel heavier. You feel heavier. Because that normal force, that push from the actual floor, from the scale. Now, obviously, when you ride an elevator, you're not actually on a scale, but that scale really doesn't need to be there, right? That scale doesn't need to be there at all. It could just be the floor. So all it needs to be, that scale doesn't need to be there. But still, it's the normal force of the floor still pressing on you and making you, go up. And it's buckling your knees, and it's making you feel heavier. That's your apparent weight. So when you are moving upward and accelerating upward, acceleration ends up being upward, you feel heavier. Because it has to be in order to move you upward and to cause you to, because remember, you're accelerating with the elevator, right? You and the elevator are going to have the same acceleration. When you and the elevator accelerate upward together, that's because the elevator floor is pushing on you. And so you have to feel heavier because that floor is trying to go through you. And of course, if we, know all this and we do if we do this formula, you can calculate all that if you want to. I'm not going to finish all the calculations here, but we know the normal force is upward. And we know so the other thing is the gravitation, Fg, that's not going to change, right? Your gravity, the force of the planet pulling on you is not going to change just because you're in an elevator or on a bathroom scale. This is not going to change because you're on the planet Earth. So that's going to stay constant. And so, in this particular example, this 500 isn't going to change, and the mass isn't going to change, but the acceleration is going to affect the normal force and vice versa. Right? Now, let's reset the scenario. Let's say that you are now going to be in the elevator. Let's say you're at rest. Say you're at the top floor and you got to go down. And so if you're at rest, normal force and gravity would be equal. But when you start to accelerate downward, you press the button, you're at rest, you're on the top floor, you start to accelerate downward. Well, what happens? Well, because of your inertia, you want to stay there. But the elevator wants to, if you're here in the elevator, you hit downward, but the elevator tries to leave right from under your feet, right? The elevator starts to move down, but you want to stay right there. But then you don't because you go into kind of a free fall, but you're not in full free fall because the elevator is still under your feet, catching you, if you will. So the elevator is easing you down as you go from rest downward. That means you're accelerating downward. Now, that means, though, let's not get confused, the normal force is not pushing down. That's not true. No, not at all. The normal force is still pointing up. The normal force is still holding you up. But the normal force is not holding you up as strongly as if you were at rest. So that means the normal force has to be less than your gravitation, right? Because if 400 is here, 500 is here, that means you have 100 newtons, net force downward. And note your acceleration, by the way, is going to be a negative sign when this happens, right? Your acceleration is negative. And then if you look at this math, 400 minus 500, that would be negative 100 if you did the math. That would also be negative. You'd have a negative acceleration. That would all work. I hope that makes sense. Now, lastly, the two other scenarios, and we have to think about these because you have to be familiar with the motion and sign of acceleration as you go. What if you were moving downward and you started slowing up as you move downward? So, this idea of the velocity and the direction of velocity is important, but what's the change in velocity? So, again, you're moving fast, you got a fast velocity downward, but then eventually you come to a stop. Well, what's going on there with the acceleration? You're slowing down as moving down. You're slowing down in the negative direction. So in that particular case, acceleration is not downward. Even though you're moving downward, but you're slowing down while you're moving downward, acceleration is upward. So how are you going to feel? Well, the whole system is moving downward, right? And the elevator, the whole elevator is trying to move and trying to slow down to a stop. But while you're in the elevator, you want to keep on moving, right? So what's the elevator do? The elevator's got to stop you from doing it. So you're trying to move down. The elevator stopped and you're trying to keep moving downward. The elevator's got to push up on you harder than as if you were standing still. Oopsie. Oh gosh. Don't do that. So you're going to feel heavier in your legs again. Oh, by the way, and I totally missed this, and I make apologies. But in the previous example, right? In the previous example, when you were at rest and hit the button and the elevator totally... No. In the previous example, when you were in the elevator, you were stopped and you hit the down button and it went down. Don't you feel lighter in the legs? Doesn't it feel like the elevator's leaving your feet? Don't you feel lighter? Well, your apparent weight would feel lighter, right? You don't feel as heavy. As a matter of fact, I can take this example and go nuts with this. What if, gosh, we, magically made the elevator disappear? What happens? Well, then you go in free fall, don't you? You'd really feel light. As a matter of fact, in free fall, you notice your normal force would completely go away. Wouldn't it? All right. You feel super light then. All right. Well, let's get back to the other example where we were moving downward and slowing down to a stop. And that means that the elevator had to catch you and stop you. That means the normal force would be higher again. Maybe you're going to feel heavier. Maybe it's back to 600 newtons to stop you.